Okay, good morning, everybody. I'm Jean, and I'm here to teach you this fantastic course about advanced visualization with ParaView. And I like the fact that the word advanced is the first word in my title, because that's what I like to do. I like to do the big, hardcore, parallel stuff, the big data, etc. We can also do the smaller stuff, but we're going to learn a lot of advanced material in this class. So the expectation, as I wrote to you via email last week, is that you have already used ParaView, at least for a few weeks, if not for a few months. I've used ParaView for, oh my gosh, almost 20 years now. We're going to go through this. So I'm quite advanced in my usage, okay? This is the organization. We're going to use part of the tutorial from Ken Morgan, my colleague at Sandia. And by the way, all the notes are ready. I'll tell you how to get to the notes on the next slide. All of you should have installed ParaView 5.7 release candidate 4 on your computer. We're going to do a lot of exercise on your own computer, but we're also going to connect to PitchDate to run client-server computation and to run batch mode computation and to run parallel computations. Okay. That's what I just said. Course accounts have been distributed. A maximum of 2 compute nodes are reserved for each of you. So when you log to date in the exercise this morning, don't ask for 500 compute nodes. You will not get them, first of all. And please be kind. I've reserved a small amount of nodes because this is September. This is 25th of September. It's the end of the allocation period at CSCS. Everybody's trying really hard to get the last they can out of their budget, so I didn't want to waste resources. There's an ETH Zurich acceptable use policy that should have been signed by each of you, and you have received an account and a password to go along with the exercise. Log in on PitchDate. You go through the front end called ella.cscs.ch. Use your own username, of course. And then from Ella, you can go to Date at the same address. On Date, you will have a home called $home and a scratch called $scratch space. This is a temporary space, and this will be live until tomorrow midnight. Don't count on it after midnight. So if you develop exercise, develop your own stuff during the next few days, the next couple of days, and you want to take it home tomorrow at the end of the class. All the data and scripts which I have prepared are in my own Scratch SNX 3000 G5. Let me find a laser pointer. That would be fast. That would be better. I have to turn this on. There we go. Okay. At the address ParaView. We will get to that. My advice is to then copy with a recursive flag all of this to your own Scratch, and then you are welcome to modify any of that. You will have to read this. This is the official documentation. It has a few more tips on how to connect your laptop to the remote machine. So here's the program, tentative. For today, the coffee, we've already done it. I will give the introduction now for about half an hour, and then we will jump right away into data format and data interfaces. We'll give lectures and a mix of interactive demonstration, etc. We'll have lunch. Then we'll talk about SMP parallelism and MPI parallelism in the early afternoon. talk about Python interfaces, do some exercise, coffee, then more exercise, and talk about custom C++ Python interfaces using Qt. And then we'll wrap up for the day until tomorrow to start with some easy stuff, animation scripting. And there will be a lot of Python, a lot, not a lot. It will be based on Python, but it's not a huge quantity, but it's something that you don't find in a manual. This is why I like to teach it, because people have a hard time to find out how to do it. Then we'll talk about volume rendering, and then the absolute best, the absolute latest in ParaView, which is ray tracing and path tracing. Just as a sample here, has any one of you done volume rendering before? Three persons, more or less. Good. Anyone done ray tracing and path tracing? One, more or less. Okay, good. So this is great stuff. I love going to the office just to do those things. We'll see what it is. So introduction, we'll go through the first pages of the tutorial by Ken. This tutorial is for, oh, did I say the PDF of my course notes are located also here in that directory. So you're welcome to copy it at some times and to follow up if you wish. I think the introduction is going to be pretty brief because, as I said, I wanted all of you to have at least had some preliminary personal experience with ParaView. So this is the ParaView tutorial written for 5.6, and I wonder if, you know what? I've already made a mistake here. Okay, there are two versions of the ParaView tutorial on the Sandia National Lab, on the ParaView website. One of them is written as text, and this is the one I have linked to into my presentation. And then there's another one which is provided as a PDF document, as a PowerPoint document, I'm sorry. So this is the one I'm going to go to. And you know what? I'm going to do just this ParaView. I'm going to search for it just like that. All right, and Ken Moreland at Sandia is one of the persons who has contributed the most to ParaView through his own development and also, I guess, providing funding through his organization for ParaView. So he really needs to get a lot of credits for ParaView. All right, so ParaView, this is about the installation stuff, so we'll go quick. What is ParaView? It's open source. This is fantastic because I like to, everything I do, I like to share it with the users. So open source, scalable, it can scale to many hundreds or thousands of compute nodes. Multi-platform, it runs on your cellular phone or on your laptop or on your supercomputer. It has a very fancy, and we would go through the details of that, execution paradigm to be able to support distributed computation. And a flexible BSD3 license, that's not to be under. And there's some nice pictures here in the introduction by Ken. There's actually two of them from CSCS here, two pictures I have made, one of them with we're going to use actually this data set here made of a molecular set. And then this is a project I had done many years ago with a company in Vevey, VA Tech. Was about turbomachinery. ParaView usage, this was last year, 135,000 downloads per year. That's a pretty good number, and it keeps growing. Data ranges, some of the landmarks, see, 15 years ago, we were already at 6 billion structured cells. And we'll talk about the difference between structured and unstructured. I hope it's already clear to you, and if not, we will clarify that. AMR is adaptive mesh refinement, so this is yet another complication in the storage of data. And then the last one was 2016 here in this list, 6 billion unstructured cell. Now, 6 billion unstructured cell is a lot more than 6 billion structured cells from 10 years ago. We'll understand through the course what those differences are. ParaView is built like this. At the base, very low level, there is OpenGL for graphics, MPI, IST, okay, MPI for message passing interface, IST for the image compositing library, etc. That's a good placeholder because now there's more than OpenGL. All the ray tracing stuff we're going to do tomorrow is based on some proprietary, actually, some of it proprietary, some of it open source libraries from NVIDIA to do rendering. On top of this, there's VTK. VTK is a C++ toolkit, a C++ library, and then that C++ library has been wrapped into Java, into Python, into other languages, and we will use the Python interface to VTK. On top of this, there is the ParaView server, and then on top of it, again, there is the ParaView client. So this is the standard application you would run on your laptop. It's a client and a server all together. PV-Python is the Python interface to the ParaView client. There's ParaView Web. There's Catalyst, which is an in situ library, which I could talk about if you are interested, but we would have to drop another topic. I have a tutorial ready for that. In situ is the ability to generate visualization content at the same time a simulation is running. And then custom app will do some of this, indeed. Development, here I wasn't lying when I said that I've been using ParaView for almost 20 years. 0.6 release 2002, I was there. Actually, it was pretty painful, if I recall. A lot of things have happened since then. GUI was rewritten. And then finally, as of ParaView 5, OpenGL 3.2 was introduced with a huge performance gain. And then from there on, it's really fun to use ParaView. There's a lot of funding coming to ParaView via ASC, via Los Alamos, via Sandia, via ECP. Some of the contributors here are listed on the left, and then other contributors on a voluntary basis are also listed here. At CSCS, this is myself. I think I will stop here. Well, the basics of visualization, I hope it's all clear to you. Going from numbers to pictures. It doesn't necessarily have to be a pretty picture. It has to be a picture that tells something about your visualization, okay? So I've put a lot of emphasis for all those years in promoting scientific visualization, not to make pretty pictures, to make pictures that are useful. Then, if the picture is also nice, we put it on the cover page of a book, and then everybody's happy. But that's not the end. That's not the end goal. Okay, let's remember this. Data types, just quickly. I hope you can see the grid lines here. Those are the so-called structured grid here on the top row, the uniform rectilinear grid. The non-uniform rectilinear grid, this is where spacing will vary in 1 or 2 or 3 dimensions, typical of those non-uniform rectilinear grids are the grids which are used for weather and climate. Very close to the surface of the Earth, we compute with very low vertical resolution. And then as we go up in the atmosphere, we can use large spacings of grids. Curvilinear is the so-called VTK structured grid in VTK. As you can see here, we have a nice cylindrical shape. You can imagine that this would fit very well any type of computation where you want to do, where you have cylindrical, spherical shapes, etc. Think about an airplane, for example. Then we have polygons, and then we have the unstructured grids. The unstructured grids are anything made of tetrahedra, hexahedra, triangles, quadrilaterals, etc., etc. And then a lot of them here are listed, a lot of other derivatives are listed. One of them which is not listed is actually points. If you do SPH, smooth particle hydrodynamics, for example, you'll only have points. If you do LIDAR, so you'll have clouds of points, many of them, for example. We can do all of this with ParaView. Okay, so this is quite interesting to know. All right, I think that's pretty much what I wanted to do with this. And then to motivate a little bit those 2 days, I'm going to show you some examples of visualizations I have made. So the first one I will show is, actually, it's never at the right place. So all right, this is the first video I want to show. Let me start again. All right. I can't get the title right. It's about volume rendering in a very large grid. And this is a project that actually took many months of development for me to get it through the final video. And when I say I made a video of it, well, I only make about 2 or 3 videos every year because it's a lot of work. But really, most of the development I do is just about developing a custom interface, developing the right colors, the right etc. So let me pause. Okay, there's a large grid. How large is it? You can't tell from the picture. So it's very thin, but it's very large, and it's about 10 billion structured points. So when I talk about big data, well, how big is big? This is big. In fact, many years ago, in the early ages of ParaView, Jim Ahrens from Los Alamos, my colleague there in the development team of ParaView, said, had a great definition for big. He said, big is what does not fit on your computer. So today, I have this laptop. Big would be 64 gigabytes of data because I only have 32 gigabytes of memory on this laptop. If I use my cellular phone, big is something else because I have an old phone. If you use Pete's date to do your computation, then big is really big because you have a lot of compute power and memory together. So this is big in the sense that 10 billion grid points fit. Well, what is the weight of a mesh of 10 billion grid points? Each scalar field is 4 bytes if it's stored as a floating point number. So we already have 40 gigabytes of data. Well, on Pete's date, the GPUs we have are the Pascal 100 GPUs from NVIDIA. Well, guess what? They only hold 16 gigabytes of memory per GPU. So to do this visualization, on the GPU, I must absolutely go parallel and develop a parallel visualization solution. We will talk some more during the visualization chapter, the volume rendering chapter. There are alternatives. I can do all my volume rendering on the CPU, and in that case, the performance is different, but I can also have more freedom to develop this visualization. So let's go through. What is happening here? Well, we have some nice, smooth animation of this block, this volume of data, because I'm going to traverse it. And at the same time I move the volume around, the flow is actually moving through. So I have a time-dependent solution. So remember, we said 40 gigabytes of data for one time step. Here I have 1,000 time steps. So we are already at 40 terabytes, right? And then we have multiple cases of, as you saw very quickly, multiple cases of simulation. So we must rerun that visualization multiple times. In fact, I'm not counting how many hundreds of times I had to generate this to make it right. Because this was actually part of a visualization showcase at Supercomputing last year. And to get it right, I had to repeat many sequences. And by the way, when you have a large time-dependent parallel simulation like this, you don't do everything in one afternoon. You do maybe some computation today, some computation tomorrow. You want to restart exactly at the same time step, at the same position in the screen, etc. And then you see here this nice, I've really managed to go into the volume to look at the turbulence in this fluid simulation. So to be able to restart or to replicate a visualization state, I must use Python. And Python is fantastic in that situation, in that it allows me to really script every single detail, every single pixel. So we will go through that. It doesn't mean we're going to do some fancy object-oriented Python programming. That's not the purpose, and that's not really useful for this context. We're going to do some simple Python using the wrapped commands of ParaView. So that kind of motivates, this video kind of motivates the discussion. Let me say one more thing. Okay, when you have 10 gigabytes of data, I don't actually load it on my computer because I cannot. But I do a lot of a lot of prototyping on my computer. What does that mean? It means that I have to use a lot of fancy tricks. Those are the tricks I'm going to teach you to be able to prepare a visualization with low resolution data, maybe on a single processor, and then you move that Python script to a large case to do your parallel simulation. And all of, so I can take any sub-volumes of this large simulation here and actually do all the prototyping on my laptop. Okay, that's one video I want to show. And then the second one is this one, which is starting right at the beginning. Okay, this is very recent. I've done this summer. This is a plunging jet, so a jet of water entering this volume of water. And here again, okay, there's some very interesting physics taking place, but I am less, actually, I'm not qualified to tell you about the physics. Professor Koumoutsakos would do this much better, but I'm qualified about telling you about all the different tricks that went into making up this video. So there is here what I said is called ray tracing and path tracing. Basically what we have, let me go forward just a little bit here. Oh, this is a good point to stop actually. Here we have a volume of water. So water is a particular material and there is light refraction through the water. Over here I have air. So actually I don't have air, I have a container. So I see through the glass container. Glass is another material that behaves differently. And then over here on this part here, I'm completely in the open space, so there's air, the normal air. All right. So we will talk about how we did this during the session tomorrow on path tracing. Another word on this is that the data here is pretty small actually, so I could do all of the visualization on my laptop. And it's important because my laptop has a very recent GPU where I could do this photorealistic rendering also in near real time. All right. So I'll stop over here for this discussion. And I'm going to jump right on the discussion of data formats and interfaces. And I'm going to use as a motivational example, yes?
Yes, please. So can you go back to the slide with the download link for this slide?
Yes, I can. So, do you mean this? Or what do you want to download? Yeah, so exactly, yeah. If you log in to Daint using your username, at this particular address, you should find the data, the script, and the PDF file of that presentation. Maybe I'll give you a couple of minutes here right now so that you can all get a copy of it. Has someone already gotten a copy of it? Is it working? Yeah, okay. Read permissions are okay. Pardon me?
My login is not working.
Ah, okay.
Yeah, we need I cheated, John, and used my CSCS
Yeah,
account, but the
me as
course
well.
accounts aren't working.
The course accounts are working because I tested them.
Okay, well, there's some problem in.
So show me the password file. I'm going to tell you what the trick is.
Okay.
I thought that wasn't very friendly, but on all those passwords, there's a dash at the end. And that dash, the dash actually is part of the password. I should have told you that. So whichever password you memorized, add a dash to it. Please try, and then we will proceed. It works, yes. Yes, okay, okay. Okay, all of you? Now, Colin, you're not supposed to cheat. No, because this doesn't do me a favor. If something doesn't work, you need to tell me right away, okay? All right, good. So each of you get a copy of the PDF, and then we'll start again. Okay, can I move forward? Yes? All right. All right, so the example I want to use here is using part of a data set, which we will use again tomorrow during the volume rendering demonstration. This is one-time step from the COLA galactic outflow simulation, kindly provided by Evan Schneider and Brent Robertson in the USA, and the NVIDIA folks who have packaged all of this for me. All right. This data set is stored as a raw volume of data. This, by the way, would be practically the easiest way to store data. And by the way, I don't mean ASCII. Of course, ASCII is easy, but ASCII output does not belong on a supercomputer platform, right? So if you have a large volume of data, you store it as binary, for example. Now, if I look at my ParaView interface, I have a reader of data for raw binary data. I have to choose the data type. So this is floating point number. I have to choose the engineness, so it can be little or big engined. And then I have to set explicitly the volume of data. So in my case here, I have said this data set is a volume made of 2048 points in the x direction, 1024 in the y and z direction. And those are extent, so they're really the indices. This is why it's 2048 minus 1, 1024 minus 1, etc. It goes from 0 to etc. If I read this into ParaView, I end up with the following information tab. I have a uniform rectilinear grid. The number of cells is 2.3 billion, 2.1 billion cells. So it's fairly large. And then I have one scalar field called image file of type floating point, and this is the range of data. And over here, I find exactly the extent I had publicized, 2048 by 1024 by 1024, and those are the x, y, z coordinates. Everything is clear here, right? You've seen this interface before in ParaView.
What's a data byte order?
What is the?
Data byte order.
The data byte order is the engineness. You know that there are two different types of computer architecture, CPU architecture. One of them is called little engined. The other one is called big engined. There's IBM versus the other architectures. It's a way of storing, for example, a floating point stored as 4 bytes. You can store byte 0123 or byte 3210 in that order in memory. That's the engineness. So I'm going to read this example using the image reader, and this would be the Python syntax: reader, image reader, file names, and my file name. And yes?
Software for this other pointer installed, for this one.
Why?
Logilink, because then I see your pointer. Otherwise, I don't see it. You know? I'm recording the computer.
Well, I don't know how this works though.
You have to install Logilink from Logitech or the Logipoint. You can do it after a break.
Okay, we will try that. Yeah. So if I open my my interface here for ParaView, this is what I get. So I select float for the data type. I select little engined. I select here the size, which is 2048. $1,024. No, I just made a mistake. I just told you that I have to subtract 1. 7. 1023. And here there's some wait time. I'm reading from a pretty slow disk, but things are going to show up pretty soon. Pretty strange. Okay. So there's the first optimization in ParaView. I've loaded a 2 billion cell grid, and by default what I see is this bounding box, and this is great. This is great because I don't want, because coloring this particular data set would already consume quite a bit of memory. I'm going to show it to you now. See, it takes a few seconds, and there is the block of data, all right? Okay. Nothing we can understand very well at this time, but that's not important. What I wanted to show you is the memory consumption in ParaView. So we have here in the view this particular panel here, which tells me that exactly 10 gigabytes of data have been consumed to read this block of memory. Now we have 8 gigabytes of data consumed here. No, actually 8 gigabytes of data consumed by the grid itself. And then the representation, the graphical representation here takes another 2 gigabytes. So I'm already consuming half of my memory here. And that's not very friendly in terms of prototyping. Okay, you'll have to agree with that. How many processors am I using here? A single one. Okay, fine with that. Now this interface is a little bit complicated because every time I have to put those numbers in. So I thought, I'm going to try to be clever, and I will choose a different interface. Instead of using the raw data image reader, I'm going to use a reader called Metafile Series Reader, which is an MHD volume. And basically, the MHD description is a very simple, very user-friendly ASCII description of your data set. And that's exactly the content of the file. So it's ASCII, you write it here. Object type, image, dimensions 3, binary data is yes. This is a little legend. Compressed data is no. The spacing 1, 1. Here are the dimensions of the grid, the element type, and the raw file number is right here. So basically, this is a solution where you can separate the bulk of the data, the binary data, into one file, and then the description of the data into another file. So that's very friendly, you would say. Well, yes, it is. I'm going to read that data. But first of all, because it's big, I'm going to go parallel. Okay, that's the first idea in mind. I'll put my glasses on to be. So you know in ParaView how to go to parallel. On your own laptop, you can say enable auto MPI. Over here. And then you can choose. Here I've decided to use a server with four instances on my own laptop. So this is not connecting ourselves yet to ParaView. If I say apply and quit, the next time I reload ParaView, ParaView will run in client server mode. And I'm going to show you what happens here. If you look on my screen, this is what is happening. I'm running MPI exec with 4 processes. I'm running PV server, which is the name of the executable for the parallel server. at a particular port number, and then I'm running the client, and the client connects to the server. This is all done locally on my computer. The same would happen if I were to connect to a parallel server outside of my laptop, so for example, Pitt's Date. So I think you have all installed a precompiled version of the executable on your laptop. It will depend on your operating system and on the versions that were packaged into the executable, but it's likely that you can also run in parallel on your own laptop. So give it a try. Give it a try. In any case, follow here the demonstration I have to present. So there's ParaView. And ParaView in parallel looks exactly the same from the graphical user interface point. I'm going to open my data, and I'm going to read my ImageD file. And there it is. Oh, well, it's probably because I read a smaller part of it, but still. See, I've told you before that creating the external surface color can be a very lengthy computation. And here I'm running in parallel, and you would say, wait a second, this is taking longer than 5 minutes ago. Something is funny. So let's look at the data. Okay, the data looks correct. It's only half of it, by the way, so I could show you the inside of it. But it took a lot longer. Well, in ParaView, you know that there is, when you run in parallel, there's this special field called VTK process ID, which will actually give a different color to each piece of the volume that is managed by an independent PV server. So by coloring my grid with the process ID, wait a second, I expected to get 4 different colors, and I only get 1. This is why it was taking forever. Let's go back to my memory view. I don't know if you can all see. There we go. I have one processor, processor 0, using 5 gigabytes of data, and processor 1, 2, and 3 only using 160 megabytes of data. So basically, there's no work balancing. Basically, only processor 0 did all the work. And this is why I get this blue-colored volume here, because I thought I was running in parallel, but actually, yes, I wasn't, but only one processor was doing the job. So I failed miserably in making that visualization. So I'm going to delete this, and I'm going to reload the raw data. Okay, I select float. Where is float? I don't see it. There's float, little engine. 2047. (2023). And we're almost there. And 1023. And something went wrong, so I better restart my thing here. Sorry about that. So file, NVIDIA, raw. Oh my goodness. Well, I will not waste time on this. The moral of the story is the following. I had a raw binary volume of data, which I could read like this. And then I thought, oh, I'm going to get smart, and I'm going to use an alternate file format, MHD, which gives me a nice, friendly user interface to describe the content of my data. But I just demonstrated to you that reading in parallel fails miserably. The reason is that that particular file reader is not capable of reading data in parallel. And now we're going to introduce the whole discussion about when can I do things in parallel, when can I not, and how do you, if you provide an interface for your own data, how do you ensure that you're selecting the correct data format? So the fact is, about data types and data interfaces, it's really, I could not count how many tens or hundreds of hours I have spent in teaching people to use the right data formats. And if we look at if we open ParaView and say open file, we have a selection of over 175 formats available today. So the first question you should ask yourself is, should I invent my own data format, or should I try to use a data format that is already supported by ParaView? If it is supported by ParaView, chances are there is a parallel implementation for it as well. So I can do big and I can do small and big data. So this would be the first reflex to have. Make sure you try to see if your data can fit into an existing format. So reading in parallel, using the raw data reader actually is supported. And this is the picture I should have been getting on my laptop here. And the data gets split very nicely among all the different available processors. So we compare basically the two different solutions we had, reading the raw data where the data gets split into parallel tasks, and reading the same data using MHD where a single task does all the work.
So John, how do you know whether a format supports parallel processing or not?
First answer is you try. So you try. ParaView crashes. It probably means that, so you're on Pete's day and you have allocated multiple nodes, but all the data was read on a single node, so you run out of memory. That's the first immediate symptom. You've run out of memory, so that's a bad sign. But there are cases like I demonstrated earlier on my laptop, you actually have enough memory, and it looks as if data are read in parallel, but they're not. And the second symptom is it gets pretty slow. It's a lot smaller than you had anticipated. And this is when you need to ask yourself some questions. Then the third thing to do is to check this VTK process ID and to color the grid by the processor ID. And here you get a good idea of what is going on. Fourth solution is you ask me. It's probably the fastest. Probably the fastest.